Hello again. Next we're going to talk about rabbits. Rabbits? I thought this was maths. Well, this is a very simplified model on what happens when you have rabbits. Now, any of you who have rabbits, whether that is you pupils or the teacher, will know that if you have more than one, what they do is they breed, and fast. So what we're going to have here is a very simplified model on how rabbits breed. Now, what I have here are some little baby rabbits. Look, aren't they cute? Look at these little baby rabbits. These were donated to me by my mathematical friend Katie Steckles, who found them. I've made a home for them. There are only two rules for what happens with our rabbits. So the first rule is that every time we move from generation to generation, the rabbits, if we've got baby rabbits, they grow up to adult rabbits. They grow up to grown-up rabbits. If you've got a pair of grown-up rabbits, like these, what happens then is they breed and they make another pair of baby rabbits. And we're going to ignore the fact that the colours of the rabbits are all different. Now, if you want to play this along, you might need to make a whole load of baby rabbits and grown-up rabbits. They could be Play-Doh or plasticine, they could be multi-link blocks. They don't need to look like rabbits. I mean, these do look like rabbits, I think these are pretty cool, but yours don't need to, if you want to play along, that is. So I'll just put a little pause point in case you want to play along with a whole stack of baby rabbits and a whole stack of grown-up rabbits. I've got 3 pairs of each. You could have more. Okay, maybe you've got your rabbits now. So here what we're going to do is we're going to count in each generation how many pairs of rabbits. So generation 1, 1 pair. Now these are baby rabbits. What happens next with babies? They grow into adults. So what happens is those babies turn into adults, and we ignore the fact that they've changed colour. That's perfectly natural. So now we have some adult rabbits. Now, what are the rules? So we had 1 pair. In the second generation, we have 1 pair. What happens next? And no, they don't die. If any of you said they die, they never die. I never said that was in the rules. Okay? So they don't die. They have some babies because they're grown-ups. So they have some babies. So I hope you're keeping track of this. We had 1 pair. Then we still had 1 pair, but they'd grown up. And then these ones have some babies, so now it's 2. So we have 1, then 2. What happens next? These ones grow up into grown-ups. And these ones are already grown-ups, so they have some babies. And I'm running out of hands. So these weren't grown-ups, had babies. So now we have 3 pairs. You're welcome to pause me at any stage. Shall we see what happens next? Right, what happens next? Well, these babies are going to become grown-ups. Some more grown-ups. These grown-ups were already here, so they have some babies. And these grown-ups were also already here, so they have some babies. Ah! So, how many pairs do we have now? A pair of babies, sorry rabbits, another pair of babies, a pair of grown-ups, another pair of grown-ups, and another pair of grown-ups. That was 5 pairs altogether. So the sequence so far went 1, 1, 2, 3, 5. How far can you take the sequence? And can you spot anything interesting about the sequence? Over to you while I rearrange my bunnies. Hello, how did you get on? So the sequence should go 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and it continues endlessly. Now, did you spot what happens? To get from the next number in your sequence at any point, 1, 1, 2, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. Every number is the sum of the two previous numbers, and that happens because every time you have a pair of children from 2 generations ago, they become the adults in the next generation. So you're kind of adding the grown-ups from one generation plus the grown-ups the ones that become grown-ups from 2 generations ago. So you're adding the 2 previous numbers to get the next one. And this is called the Fibonacci sequence. It occurs in many, many ways and forms in nature, and mathematicians will see it in all sorts of places. The Fibonacci sequence. Hello again. So for this next piece, you are going to need 3 objects. 3 objects. Those are called A, B and C. Now for me it's very obvious. A for apple, B for banana, and C for carrot. I'll give you the chance now to find some objects if you don't have them already. It doesn't matter if you don't have an apple, banana and carrot. 3 pieces of paper with A, B, C written on them will be absolutely fine. Now, what I want you to do with them is to try and work out how many different orders these could be placed in. So for example, one order that you could place these in is apple, banana, carrot. So there's just one order that you could have them in, but you could also have the order apple, carrot, banana. There's 2 ways that you could order these. What I would like you to try and tell me is, how many ways are there for ordering these, and can you list all the different orders? Over to you to have a go. Hello. How did you get on? Now, here's a way that you could do this systematically, because working systematically is best. You could have the apple on the left, banana, A, B, C in the obvious way. And then if I keep the apple where it is but swap the other 2, I get A, C, B. That's all the ways with apple first. So now I'm going to switch it, so bananas first. And then go to apple, so I get B, A, C. I'm going to keep banana first and swap the other 2. That is B, C, A. Next, I'm going to put the only one that first that hasn't been first, which is carrot, and go carrot, apple, banana, C, A, B. And then finally, we go C, B, A, which hopefully none of you are thinking at the moment. So there are 6 ways altogether, 6 ways. Very well done if you got 6 ways. Now here's a real challenge. We're going to add something else, D. I didn't have a foodstuff beginning with D. In fact, I forgot to pack anything. But I have got this hand sanitizer, which is delicious smelling. So this is my D. Right. We now have 4 objects, A, B, C and D. In fact, I don't know why I'm holding them up. Hopefully you can see those on the table. A, B, C, D. How many orders can they go in? Here's a real challenge. Can you work out how many orders without doing them? Don't get me wrong, it's great fun to do them, but can you work it out without? Hello, welcome back. Right, I'm going to attempt to demonstrate all of the possible orders. Goodness me. So, keeping apple first and keeping banana here, I could have C and D, or I could have D and C. So there are 2 ways. Alternately, I could keep the apple there, move carrot to first, and then I've got 2 ways to have these. So that's another 2. Or I could have B first, leaving apple first, and keep banana and carrot here. But I could swap those 2 ways round. So that's another 2, giving 6 ways. Now, that was just with apple at the front. But there are 4 things that could have been on the front. So actually, for each of those 6 arrangements, there's now 4 different fruit that I could have on the front. 4 times 6 is 24. So the right answer, if you got it, well done, is 24. Now here's the quick way. Imagine instead of ordering them, I'm putting them into slots. So imagine I had 4 slots on my table. And how many different items are there that could go in the first slot? Well, there's 4 items to start with that could go in the first slot. But once you've put them in, so that was 4 ways, once you've put one in, there's only 3 things that could go in the next slot. So in goes 1. 4 times 3. Now for each of these, there's only 2 ways that the next thing could go in, either D or C, or A this is actually. And then once you've done that, there's only 1 thing that can go in the 4th position. So it's 4 ways times 3 ways times 2 ways times 1 way. 4 times 3 times 2 times 1 makes 24. And that operation, 4 times 3 times 2 times 1, is called a factorial. It means you take a number and you multiply it by every number on the way down. So when there were 3 items, it was 3 times 2 times 1. 3 times 2 times 1 is 6. If there were 5 items, E for exciting book, there would be 5 times 4 times 3 times 2 times 1, which is 120. That's called 5 factorial. You wouldn't want to list all the ways of doing this. It's very long and complicated. Now, factorial numbers, you'll notice they get big quick. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial was 24, and 5 factorial is 120. They get big quick. First question is, how many people are there in the world? Do you know roughly how many people there are in the world? So it's about 7.5 billion, which means 7 or 7,500 million. What number factorial makes that? How many ways could we order items to get up to 7.5 billion? Well, incredibly, 13 factorial is about 6.5 billion, which is incredible, really. And what that means is, if you went outside, just stepped outside now, and then look around, there'd be lots of people outside with you, and then everyone who was outside got into groups of 2. Hopefully you can do this, maybe safely with social distancing, depending on when this video goes out. Let's say you went out to the playground and everyone got into 2s. And then those 2s got into 3s. You'd have 6 per group. So you got into groups of 3 lots of 2. And then those 3 lots of 2 or 6s got into 4s. So you'd be in groups of 4 lots of 3 lots of 2. Groups of 24, which is kind of nearly a class, I suppose. You might be running out of people in the playground now. And though those 4 lots of 3 lots of 2 got into 5s, so 5 lots of 4 lots of 3 lots of 2, you'd be in groups of 120. This would be getting genuinely difficult now, but it could be done. If you kept doing that and teaming up in groups of groups of groups, by the time you'd done that 13 times, everyone in the world would be involved, which I find quite incredible. I'm just going to give you a little, one of my poems again, all about this. It's called Do the Factorial. As I've said to you, sometimes I do a lot of singing with my maths. I thought it would be weird if I sung to you a cross video link. So I'm going to read the poem instead, called Do the Factorial. It's time to put on your dancing shoes. Link hands with your partner and dance in twos. Other hand in the air like you just don't care. Everybody in the world's dancing in pairs. Now take these pairs and group into threes. You can do this part with relative ease. Not a problem on earth this dance can't fix, with the whole world dancing in groups of 6. When these new groups move into 4s, you'll probably need to step outdoors. The whole world moving like a dream, with 24 dancing in every team. There'll barely be space to waltz or jive when the 24s move into groups of 5, because 5 times 4 times 3 times 2 makes 120 in every crew. Now continue the pattern through larger sets, see how big factorial numbers get. You'll see by the 13th iteration, one dance for the whole world's population. Because 13 times 12 times 11 times 10 times 9 times 8 times 7 and then times 654 times 3 times 2 makes 7 billion, give or take a few. Imagine that in 13 moves, the whole world locked in a single groove. It's unlikely to work, I fear, but hey, it was a nice idea.